Yeah, so thank you for inviting me to speak. It's great to be back here as a UBC grad. I worked for Parisa Mercotovandi when I was in the department, so it's nice to see this institute grow from the time when I was here. Yeah, so today I want to tell you a little story about some work we've been doing in paper packaging at FPI. I just want to throw this up in case some of you are not familiar with what we do. So we're a non-for-profit research organization. We have offices in Montreal, Quebec City, and Vancouver. We're actually just down the road on East Mall. And we support Canada's forest industry. So that includes things like pulp and paper, wood products, bioproducts. And today I'm going to tell you some of the work we've been doing to support our members in pulp and paper, specifically in the paper packaging area. So we've been working in this area for a while, and lately we've been focusing on applications for food packaging. So you might think of food packaging, you typically think of plastic, but of course paper has a lot of applications in this area, but it doesn't really have any barrier properties. So we need to add coatings or change the properties of paper to make it applicable here. So what are the kind of barriers that we need for food packaging? So we can think of things like oil and grease resistance. That's really important. Here in the brackets, I'm just putting some of the characterization tools that we would use to quantify these kind of properties. Also, liquid water can be important. You can think of things like coffee cups, for example, would need that. And also barrier against gases. Oxygen is particularly important for food because it causes food spoilage. And the one I want to talk about today is resistance to water vapor. So that's also really important for not only improving barrier against food spoilage, but also keeping the properties of dry foods. For example, you can think of you don't want your chips to get soggy, for example, in storage. So I'm going to be talking about WVTR today. That's water vapor transmission rate. That's how we measure this barrier property. So barrier coatings are really key for this area. If we want to make paper useful for any of these properties, we need a coating to be able to do that. So here's just a graph of some of the properties that are needed for different food types for oxygen and moisture barrier. So you can see in the top left corner, you have things that don't really need a big barrier. That's like fruit packaging and stuff like that. And all the way down to the bottom corner is a higher barrier. So you want WVTR, oxygen transmission rate, to be lower. It's better, obviously. But uncoated paper sits way in this corner. So it really doesn't have any barrier properties. And we really, for entry-level food packaging, we need to be somewhere around here. So that's less than 10 for both oxygen transmission rate and water vapor transmission rate would be sort of an entry level for like dry goods storage. So we entered this space a long time ago. One of the first things we did when we started looking to water vapor barrier specifically was assess a bunch of commercial coatings. So there are commercial coatings that are available that are marketed for this purpose. And typically, they're based on, of course, fossil-based polymers. Polyacrylators, styrene latexes are particularly prevalent in this area and are the ones that have the best properties. So we tested a bunch of these in our own lab, and other people have done the same. So although the polyacrylate type latexes are really good for water vapor barrier, there is some issues with them. One of them is that they can impact the recyclability of the paper. Obviously, we'd like to be able to reuse the paper if we can. And then, of course, the environmental concerns of using a fossil-based polymer, things like biodegradability. What are you going to do with the coating once the lifetime of the packaging is up? So when we got into this project a couple years ago, we wanted to try to see what could be done with bio-based coatings and see what kind of performance you could get if we could compete with these fossil-based coatings. So we really took this process right back to the beginning. So we did a literature search, looking at the market, and identifying both natural and synthetic bio-based materials. We looked at several different families of them, specifically honing on those that might have good properties for water vapor barrier, and then doing our material selection process. And really, our process is focused on things that are going to be practical, low cost, and effective for short-term implementation in industry. So we really want to look at what are the coating technologies that could be applied with the kind of technology that our member companies have. So once we selected a few materials, we started a formulation design. We have made over 5 formulation families, lots of formulation types, and we do quick performance testing. So this is hand draw down coding on paper and WVTR testing just to benchmark the performance first and see which of these families is really going to be applicable. And we identified one family as the front runner in this. It's a 100% bio-based, aqueous-based coating formulation. And it reaches our own targets, which were fairly conservative, which is WVTR less than 50 grams per meter squared per day, which is still, you might remember for the bidding, a bit high, but we just set it conservatively to start. And really here, the suitability to scale up this formulation and apply it with industrial relevant coating technology was the main driver for choosing this formulation type. So there's a lot of work that went into optimizing this formulation. I don't have time to talk about it today, but we have reached the sort of scale up and pre-pilot scale. We're not quite at pilot trials yet, but we have scaled, from like small vial scale all the way up to kilo scale in lab now. And we do anticipate this would be easy to get multi-kilogram scale in quite a short period of time. So because we were able to scale this quite quickly, we have been able to do some roll-to-roll coating trials. And this is helped by this new piece of machinery that we installed this year. It's a versatile coating machine for laboratory. This is abbreviated VCML. This is at our laboratory in Pointe-Claire near Montreal and Quebec. It's a really nice piece of machinery. It can do full rolls of paper, and we have several coating heads, so it can try a bunch of different coating technologies, also printing technologies. It also has an inline corona treater and a laminator, so it's really useful for our packaging applications. So for this trial, with our coating, we chose a bleached, uncoated kraft paper. This is a paper that comes from one of our member companies. And we also chose to coat by reverse gravure, which is a relevant coating technology that is used for these kind of coatings. Unfortunately, although this coats really well, we can't get a super high coat weight on a single pass just because of the solid content of our formulation. So because we had the corona treater, we were able to treat the surface after each pass and increase the coat weight that way. So that was really nice to have. So we were able to get several rolls of paper this way quite easily, just within 1 or 2 days. So in terms of performance, it's quite good. We're reaching WVTR less than 50 at coat weights, slightly above 12 GSM, which is not too bad. But you can see as soon as you start to drop the coat weight, the performance decreases. This is pretty typical. We have benchmarked commercial formulation, one of the polyacrylates that I mentioned. And you can see we're still a bit far away from reaching the performance of those types of formulations. Those can typically reach a less than 10 at a slightly lower coat weight of around 10 GSM. But this is really promising so far. So just to summarize, like I said, we have reached our own more conservative target, which was less than 50 at coat weights of less than 20 GSM. These can be coated easily on pretty lightweight papers. And although this is still, not the best performance, it's still over 100-fold decrease in WVTR compared to the uncoated paper. We're able to coat roll to roll at reasonably high speeds. It's reasonably easy to scale. We're at kilogram scale now. And it's 100% bio-based ingredients. They're also food contact safe and biodegradable. So some of the drawbacks, like I said, it's still not reaching what would really be the entry level for like a dry goods packaging, which would be less than 10. Creasing does affect the performance as well, which is a really important property. I didn't have time to talk about it today. But we do have some tricks to get around this now. But really, overall, we're still a little bit far away from reaching the same performance as commercial-based coatings that are fossil-based polymers. So there's still some work to be done here, but it's really promising, especially for 100% bio-based coating that can be applied really with industrial relevant technology. So with that, I just want to thank the people that helped on this project, as well as our funding agencies, and of course our member companies for providing paper samples to us. If you're interested in this work and you want to know more, you can reach out to me, or you can reach out to our project lead, Lynn Cormier. So thank you for your attention.